I will do, sir.
Okay. Okay, you can record now. Okay, so let's start. So last time we were looking at magnetic properties of iron, and and of course we saw that iron block that we wanted to look at, which is made up of cubic lattice, with every lattice point having iron with some magnetic moment due to d electron would be sitting, and we want to ask a question as to how does iron undergo paramagnetic to ferromagnetic phase transition at reasonably high temperatures, about 1000 °C. Okay, and we wanted to study whether this system, we wanted to see whether we could write down a model which would kind of describe this particular transition well enough. Okay, and as I said, that requires us to make drastic simplification, because iron has many other properties, that it's a good conductor, it would have some kind of resistivity properties and so on, which are of no consequence right now when we are looking at only the magnetic properties. So therefore we are ignoring things which are related to, say, conduction band electrons or lattice vibrations and stuff like that, and had simplified the model where we replace the Heisenberg spin by a spin which would take only two values, +1 or -1, which is kind of a classical two spin state. Okay, and when we looked at this system, we said that, like, we could write down a Hamiltonian. We should try to give a description of this system in a kind of compact way. Okay, now of course this Hamiltonian is a model. Okay, in the sense that, like, in realistic system the spins could be interacting in a much more complicated way, but if a model can capture the behavior of the entire spin system, that is good enough actually. Okay, so the simplest model that we thought of was that the Hamiltonian contains a term which is HI/SI, where HI is the external magnetic field, which talks to the spins sitting at every lattice site. Okay, so this kind of Hamiltonian is such that the individual spins at lattice don't talk to each other, all of them talk to external stimulus. Okay, and we chose HI to be the magnetic field seen by a spin at site SI. Okay, then we said, like, that you could generalize this Hamiltonian by allowing the nearest neighbors to talk to each other, and that's what this angle bracket says. And we wrote down a term Jij SI where SI is a spin at ith site, Sj is a spin at jth site, and besides having the interaction with the external magnetic field, they could talk to each other if they are neighbors. Okay, now we of course decided to simplify this model further by saying that Jij need not depend on Ij, it may be independent of Ij, it could be same for as long as they are nearest neighbors, and that is some number j, such that we can pull out this Jij from this summation. Okay, similarly, if you apply, say, uniform external magnetic field, then you need not worry about Hi. You could just replace Hi by H without worrying about how the spin at ith site feels the magnetic field, because we are essentially assuming the magnetic field to be uniform and constant in all directions. Okay. Okay. Then what we did was we looked at the simplest case, namely setting J to 0. So that is like spins don't talk to each other, they talk only to the magnetic field. And in that case, we could just write down the partition function in a simple way. It was just product of the partition of states, partition functions for individual spins, because spins don't talk to each other, spins only talk to the external magnetic field. So the possible states that spins could have due to external magnetic field would be, or rather energy, would be either E, which is proportional to H, or E, which is proportional to minus H. Okay, and therefore you get either minus beta h or either plus beta h. Okay, and just take a product of all those states and you get this 2 times cos hyperbolic beta h to the n. Okay, we then use this to determine free energy, which is just the log of this partition function divided by beta, and using the free energy we determine the magnetization. So magnetization is actually in some sense a response of the system when you change external magnetic field. How does the free energy change if you change the external magnetic field? And we found that this dependence, since we had exact partition function, this dependence is like a tan hyperbolic is a tan hyperbolic function, tan hyperbolic beta h. Okay, and because it is tan hyperbolic beta h, we said that this implies that this particular model that we are looking at describes this paramagnetic system, because if h is positive, then tan hyperbolic h is positive and therefore m is positive. Okay, so therefore positive h gives you positive magnetization. On the other hand, negative h gives you negative value for tan hyperbolic h, for example, and therefore it gives negative magnetization. So therefore magnetization is always proportional to the magnetic field with a positive coefficient. Okay, so if magnetic field itself is negative, then of course magnetization would change sign. Okay, so that kind of behavior is what is called a paramagnet, and that's why this model correctly reproduces the paramagnetic behavior of the system. Okay, then we wanted to ask a question: what if we turn on J? So if J is not equal to 0, then our Hamiltonian is the one that we had written down, which is H equals minus J summation over nearest neighbors Si Hj minus H times summation over I Si. Okay. Now, of course, there are various possibilities here. At least two possibilities here, and that is that either you can choose J to be positive or you can choose J to be negative. Okay, and they give you two different kind of magnetic states. Okay, but at least for our discussion, we are going to restrict ourselves to J to be positive. Okay, uh, and if you take J positive with minus J Si Hj kind of piece, you get a state which is called ferromagnetic. On the other hand, if this with the same Hamiltonian, if you choose J to be negative, then it gives what is called an antiferromagnetic state. Okay, which is also an interesting system. It has been observed in nature, and in fact, it has many more interesting phenomena occurring in them than probably the ferromagnetic system. As I was mentioning about the high TC superconductors, yes, in the previous class, high TC superconductors in the so-called undoped state are actually antiferromagnets. Okay, so if one wants to mimic those systems without where you don't dope, the system becomes superconducting only if the system is doped. But without doping, it would be a insulator, antiferromagnetic insulator, and that could be mimicked by a Hamiltonian of this kind with J negative, for example. Okay, although the system is more complicated because, as I said, uh, it's not like pure iron kind of stuff, right? You have copper oxide, you have some rare earths sitting around. Hello.
Yeah, so
Yeah.
Sir?
Yeah. Sorry, got disconnected. Yeah. Unfortunately, HRI internet is not very reliable. Uh, although in the meeting people talked about whether students would have good internet connection, some of us were dead sure that most of the problems would come from HRI internet, not so much of internet connectivity available to students. Anyway, don't quote me on this. Okay, can you see the screen now?
Yes, sir.
Okay. So let's get back to the Ising model. We are going to implicitly assume that J is positive, and I'm not going to mention it anywhere here, but that is something that we are going to use. Okay, because the reason is simple, because we want to look for ferromagnetic state. Okay, now let me kind of mention why positive J corresponds to ferromagnet, and the reason is that like ferromagnetic system would have is a system which has large magnetization, large magnetic moment. It's like a magnet, right? It has a uh, the system itself has some kind of a large north and south pole, and if you keep it anywhere, it produces a reasonably large magnetic field. That's what it is supposed to do. If you want to get large magnetization, then you would want the spins which are responsible for producing magnetization to orient in the same direction. Okay, so if you have Si and Sj pointing in the same direction, okay, then uh, it doesn't matter which way. Both of them are +1 or both of them are -1, it doesn't matter. This product will always give you a +1 answer. Okay, if this gives you a +1 answer, if J is positive, then spins pointing in same direction would lower energy because of this minus sign. Okay, whereas if J is negative, then spins pointing in opposite direction would lower energy. Okay, so therefore, if you are looking for lowest energy configuration which produces large magnetization, then you would be interested in a system where the way the Hamiltonian is written minus J Si is J, you would want J to be positive such that spins pointing in same direction would lower energy. Okay, so that is why we are going to choose J positive, because we are looking for a ferromagnetic system. Now, if you want to look for anti-ferromagnetic, of course, we will flip it, because we would want spins to prefer uh, oriented in opposite direction, for example. Okay. Okay, good. So another thing, of course, we could have in these kind of models is to have another term which is like J prime Si is J prime, where uh, J prime is not a nearest neighbor, but it's a next nearest neighbor. Okay, even those kind of using models have been studied. Okay, so of course, if you are studying model which has the next nearest neighbor interaction, it is kind of natural to assume that it also has nearest neighbor interaction. So that is a kind of model which will have both the interaction, nearest neighbor as well as next nearest neighbor interaction. Sorry, I should have said next to nearest neighbor here. Okay, that's a typo. Uh, okay, so uh, these two sentences sound really odd. Okay, fine, but I'll correct it. Okay, this is next to nearest neighbor interaction and so on. We could have a higher order uh, interactions also. As I said right in the beginning, that the realistic system, of course, spins may be interacting with not just the nearest neighbors, but next to nearest neighbors, next to nearest neighbors as well. Okay, but it is not necessary to actually model or write down a model Hamiltonian with all these interactions taken into account, because if you are trying to study certain robust behavior of the system, they may not depend so crucially on how many interactions that you really introduce. Okay, certain uh, specialized or certain specific information that if you want as to what is the contribution of next to nearest neighbor interaction to, to say energy or to say magnetization and stuff like that, in that case of course it would matter, because you would be looking at very specific effect. Okay, but a generic structure, the robust structure of the system, may not require these kind of nuanced detailed models to pick out the behavior of the system. Okay, fine. So the free energy of the system, of course, would be written as minus kBt times log of the partition function. Okay, and this partition function, of course, would involve some or all possible spin configurations. Okay, and now, unlike the earlier model where you had only h times summation si term, now you have this nearest neighbor interaction term also, and in that case, there are many such spin configurations that are available. Here, of course, we knew how many spin configurations were available. They were just 2 to the n. Okay. In this case, of course, the spin configurations that you could have is part of 2 to the n, but they would kind of contribute different sets of energies. Okay, fine. Now, if you want to solve this model exactly, okay, then exact solution to this model in arbitrary dimension, say d is any arbitrary integer, is still an open problem. Okay, yeah, this model hasn't been solved. This is probably, like, one of the simplest model that you can think of, that at every lattice site you have a spin degree of freedom which can take value +1 or -1. I mean, only thing simpler that you could have is object which should take only one value. Okay, but that is a kind of boring object, simply because it doesn't have any other option, uh, and therefore the Hamiltonian would be kind of uh, a simple counting or combinatoric problem. Okay, here of course it is little more than just combinatoric issue. There is some kind of energy involved if the spins are either pointing in the same direction or in the opposite direction. Okay, in spite of that, this problem is not exactly solved uh, in arbitrary dimensions. Okay, however, for d equals 1 and d equals 2, this model can be solved exactly. Of which d equals 1 solution is kind of easy. We will in fact do it in the class at some point. Okay, uh, d equals 2 is non-trivial, but nevertheless it is exactly soluble, and it was solved almost 80 years ago. Okay, so maybe little more than 75 years ago for sure. Okay, by Ansager. Uh, okay, so but what we will try to do is not even attempt to kind of get exact solution for even for a low dimensional case. First of all, we actually want to solve this problem for arbitrary dimension. Okay, and therefore, given the fact that exact partition function is not known, we won't be able to kind of study thermodynamic properties of the system in arbitrary dimensions uh, in an exact fashion. Okay, but there are several techniques which allow you to get approximate answers to the problem. Okay, and the idea of is that we will start with the crudest possible approximation, which will give us some picture as to how the system is going to behave. It will produce some numbers which will, simply because the approximation is crude, those numbers wouldn't agree with the experiment, but we don't care. Okay, we would kind of figure out as to what is the disagreement, and uh, how does the disagreement depend on how many dimensions in which you are working. Okay, that is the kind of analysis we will do, and given the fact that the approximation that we are doing is very crude, okay, we would ask a question: how do I improvise upon that? Okay, or at least can one write down a microscopic theory which would produce this kind of crude approximation? Okay, one can after that ask a question as to how I improvise on that microscopic theory, uh, which would kind of give me more accurate answers, and also give me more detailed information about the system. Okay, so that is the kind of approach that we are going to take. So at any given point whatever we are doing is still approximate, but it is better than the previous example that we studied. Okay, so now that we are studying the first example, first or now that we are making the first attempt, our first attempt is going to be very crude, and the second take on that would be better than the first attempt, and so on. Okay, that is the general approach. Okay, good. So I mean, you may even say that like it is almost like a historical approach, in the sense that like uh, systems were studied in a crude way first, and then they were kind of improvised by developing new techniques and learning how to apply those techniques to these kind of systems. Okay, so we already have some information about the system, and that is, if you set j equals 0, uh, magnetization is like tan hyperbolic beta h, and that implies that the system behaves like a paramagnet. Okay, fine. Uh, Now, if j is not equal to 0, okay, then the orientation of any spin that you want to look at in a system will be affected by the orientation of the neighboring spins. Okay. Now, suppose you are looking at one-dimensional Ising model, then you pick any random spin in that one dimensional system, it typically has two neighbors, unless you are really looking at the end of the line spin, but otherwise it would have two spins as neighbors. Okay, but if you go to say two dimensions, then it depends upon what kind of lattice you are looking at. If you are looking at say square lattice, you would have four neighbors. If you are looking at say triangular lattice, then you would have three neighbors, and so on. Okay, so that is how the system is kind of going to give you different kinds of neighbors depending upon how many dimensions you work. Since we have decided to use cubic lattices, or maybe I should use the word hypercubic lattices, because if you are in arbitrary dimension d, then it's not an ordinary cube, but it's a hypercube. Then in the hypercube, nearest total number of nearest neighbors is 2d. Okay, because in every direction you have two neighbors, and there are d directions, so there are 2d neighbors. Okay, now uh, yeah, so now these 2d neighbors are going to affect how this particular spin that you are looking at would behave, because it would this spin would try to lower its energy with respect to the configuration that the 2d neighbors have. Okay, now of course it is not like this is that only these 2D neighbors are trying to effect on this particular spin. This spin and all other spins of some neighboring spin are also affecting the neighboring spin. So it's kind of, a trade-off between spins, and how fast they kind of equilibrate depends upon how big is the J value. Okay, that is how this system would, actually would evolve. Okay, now one may think that, like, okay, the term is really quadratic in spin, how difficult can the system be finally? If I want to write down e to the minus beta h kind of piece, then that piece would contain term quadratic in spin, and we know how to handle systems which are quadratic. But it is not exactly true, in the sense that, like, spin is not a basic degree of freedom that we kind of would like to do if we want to say write down a path integral for studying a system of this kind. I suppose you have studied path integral in quantum mechanics already, right?
Yeah,
Yeah.
some.
Okay. Okay. So one could of course generalize that to quantum field theory. It may not be done in QFT1 course, because QFT1 mostly concentrates on canonical quantization, but in QFT2, of course, you will learn uh, how path integrals would be used. We will kind of have use some glimpse of path integrals here. We will just do the things that are essential for us, not do the full rigorous quantum field theoretic path integral in this course. Okay. Nevertheless, although the system may look simple, it actually effectively couples all spins to all spins, because ith spin is coupled to all its neighbors, but its neighbors are coupled to its own neighbors, which kind of takes you a little out to next to nearest neighbors, and then next to nearest neighbors, and so on. So the system seems to be coupled in a non-trivial way. Okay. Now we want to ask a question: if in that situation, how do we go about studying a system of this kind? And the crudest approximation, I shouldn't use the word crude, at least if some condensed matter physicists around wouldn't like it, but the one of the simplest approximation that you could do is what is called the mean field theory. Okay, uh, so the idea of the mean field theory is the following: that uh, that we do not keep track of how all individual spins would behave when you have the Hamiltonian written out there. Uh, Remember, Hamiltonian of course contains in kind of interaction of every spin with all its neighbors, and every spin interacting with the external stimulus. Okay, but when you are trying to study the system, you don't really look at how individual spin is behaving, how individual spin is contributing energy to the total system, and so on. Okay, in the mean field theory approximation, what you do is that you say that, like, if you pick any spin at random in the system, okay, then that spin would feel the effective magnetic field generated by all the spins in the system. Okay, so there is an overall effect generated by all the surrounding on a particular spin that you are looking at. Okay, now the spin that you want to look at is picked at random. Okay, so whether that spin is at ith site or at jth site doesn't matter. Okay, it would still see an overall effect generated by all the other spins. And as I said, that in spite of having the interactions which is nearest neighbor, next to nearest neighbors are still affecting the spin, because they affect the nearest neighbors and the nearest neighbors affect this spin that we are looking at. Okay, so therefore the mean field theory basically postulates or proposes rather that uh, if you look at any arbitrary spin in the system, single spin in the system, then that spin sees uh, an overall effect of the entire system, or an averaged effect of the entire system. Okay, that averaged effect that any arbitrary spin would see itself is called the mean field. Okay, now, so now what we are going to do is to say that instead of having complicated interaction like si dot j si is j summing over all nearest neighbors, we will say that like every individual spin, besides seeing the external magnetic field, also sees an overall effect generated by all other spins inside the system. Okay, and therefore this overall effect is of course going to be j dependent, because that is the piece which is going to make any individual spin realize existence of any other spin in the system. Okay, fine. So what we are going to interpret is that the mean field that we would get is something we would call an effective magnetic field. Okay, so the total magnetic field that you would have is H plus H effective. Okay, is that fine? So H effective is a mean field generated by all spins in the system influencing a particular spin. Okay, now whatever spin you choose has nothing very special. It's not like it has any special significance. Any spin that you choose would have the same behavior. Okay, would still see the effective magnetic field. Okay, fine. So we would therefore say that the effective magnetic field is going to be proportional to the total magnetic moment of all other spins. Okay. Now we really don't know what is the total magnetic moment of all other spins. So therefore, many of these calculations in mean field theory, on what is called the mean field approximation, are done self-consistently. Okay, you get an expression where left-hand side involves a quantity, some quantity that you want to observe, but that quantity depends on a function of the same quantity. Okay, we will see it in a few minutes, in fact. Okay, so therefore what you need to do is to kind of take left hand side, take right hand side, and ask under what condition that these two sides are equal. And if that happens, it doesn't happen all the time. Whenever that happens, then you say you have a non-trivial answer. Okay, and use that answer to interpret what is the state of the system. Okay, that is the approach. Okay, some kind of a self-consistency would be kind of imposed on the system. Okay, so as I said that as a result of this effective magnetic field, every spin will feel two fields. Okay, one is external and one is the mean field H effective. Okay, but as far as the spin is concerned, the spin effectively feels kind of a similar effect. Okay, so in some sense, whatever the Hamiltonian that we had written down, which was a sum over Si times Hi, and we wanted to set Hi to be just uh, some constant earlier. Okay, now this Hi won't be constant. Okay, the reason why it won't be constant is because there is a constant piece coming from the external magnetic field, which is what is written as H here. But then there is an averaged contribution. Okay, so you take this interaction. Hold on, I don't know how to do this. Yeah, so what you do is that so you replace this H times summation SI piece by HI, and HI contains multiple terms. Okay, these multiple terms that we are writing down are coming from the following thing, that suppose you have decided to concentrate on the spin SI, then you could sum over all Sj, which are nearest neighbors of SI, okay, but contribute, that sum could contribute some fixed value, okay, that fixed value would be called the average value of Sj, okay. Then Jij times Sj, now of course Jij could be the same value for all I and j, in that case it would look like this j, okay, but even if it is not, you could still keep that. Then the effective magnetic field seen by Si is Jij times average value of Hj, sum over all j's, okay. If you do that, then Si essentially sees a linear coupling, okay, unlike this Hamiltonian, which would have had a quadratic piece, Si interacting with Sj. With this mean field approximation, Si only talks to the effective magnetic field, okay, and effective magnetic field is generated by average value of Hj. The last piece that I have written down basically tells you that what I have written down is exactly this same piece as this, okay, because average value of Sj times Jij is actually subtracted out here, okay. So if you put this back in the Hamiltonian, you get this Hamiltonian back, okay. Only difference is that now we interpret it in a little different way. We say that the magnetic field seen at the site I is the uniform external magnetic field plus the H effective seen at site I plus fluctuation of the mean field from its average value, okay. We are going to ignore this at first go, simply because we would like to study the system within the mean field approximation itself. We can ask what is the effect of the fluctuations, and if the fluctuation take us away from mean field approximation, then we would say that the mean field approximation is not very stable, and it would lead us to kind of a the perturbation would lead us to a new description of the system, okay. But that we can kind of set aside for the time being. Let's try to see what the mean field is doing for us, okay. Is this point clear?
Okay, sir.
Okay. The reason why I want this point to be kind of, I want to pause here simply because this is a crucial statement of mean field approximation, okay. Everything else kind of follows in some sense trivially, okay. In fact, we will see that after this we will just write down results because we have already computed the results, okay, without doing mean field, okay. But the main point is this, that you basically assume that every individual spin interacts with some effective magnetic field, and therefore the Hamiltonian takes the form that we have already solved, okay. Good. Yeah, so this is something I had just said, that if Jij is J, then you can just pull it out, but otherwise, this effect will still be like this, okay. We are going to ignore the fluctuation pieces. Okay, this is also something I had mentioned, that if you are working with the Ising model in d dimension with a cubic lattice or hypercubic lattice, you would have 2D neighbors, okay. So if you have 2D neighbors, then you could ask the question, what is the value of Hi for a hypercubic lattice, okay. And that is kind of easy to see. This sum over J would be over 2D values, okay. So therefore this sum would involve a factor of 2D times J times the expectation value of this all the nearest neighbor spins, which would give you an average uh, kind of magnetic field, okay. But that magnetic field comes from the magnetization of the system, okay. And therefore we would kind of replace this and by magnetization, and therefore HI would be external magnetic field plus 2 times D, which is the dimension in which we work, times the average magnetization that we get from the nearest neighbors times J. Okay, fine. But like once you have figured out what HI is, then we have already solved this problem because, okay, so I don't move this, I move this one, okay, because we have solved this problem here, that if your Hamiltonian had J equals 0, okay, then your partition function would look like this, okay, and if you do that, then your magnetization takes the form like that, okay. Only difference now is that here the magnetization was tan hyperbolic H by kBt. Here your magnetization would be tan hyperbolic Hi by kBt. Okay, because that is the magnetic field seen by the spins. Okay, and if that is the magnetic field seen by the spin, then that is what would be the argument of tan hyperbolic curve. Okay, now the difference between this system and this system is that Hi itself depends on magnetization. So therefore you get an equation where left hand side is all magnetization and the right hand side is a function of magnetization. Something which I was telling you just a few minutes ago, that you get a equation of this kind, and clearly this equation would have a solution only if you try to plot the left hand side and plot the right hand side, and if the lines sorry, not lines, but if the loci intersect, then you have a solution. If they do not intersect, you don't have a solution to this equation at all. Okay, does that make sense? Yes. I cannot hear you well. H, a, sorry, I can't hear. HI what?
You have written HI equals to H plus 2D mj.
Yes, that is right. Yeah, that's right. So what is the question? Oh, so what I was saying was that the HI is that I have written up here, okay, it's just a rewriting of the full Hamiltonian. Okay, so let's kind of go down a little. The full Hamiltonian is right here. Okay. What is? Hello, I can't hear. Yeah, so I was saying that this HI that I have written up here on the screen, okay, is same as the entire Hamiltonian written down in the split screen. Okay, it is just written in a little different way. Okay, so what you do is that you write down J S J, some more J. Sorry, too many J's. Okay, capital J. Let's forget about it. Some more small J S J can be written as some more small j average Sj plus Sj minus average Sj. Okay, so this is like just adding and subtracting average Sj value, right? Is it okay? So this term that is written here as Hi is same, and of course, if you couple that to Si, then that expression is same as this Hamiltonian. We haven't done anything, okay, so far. Okay, we have just added and subtracted some piece, but like, you can always add plus 3 minus 3. It shouldn't affect any result. Okay, what happens next is the important thing, and that is that we say that the fluctuation is J minus average Sj is a fluctuation from the average value of the spin. Okay, if we say that Sj minus average Sj is small, okay, then we can ignore the third piece in the Hi and just concentrate on the first two pieces. Okay, can you hear me? Okay, okay. Now, once you know that, then you could ask a question: how many of these SJs which are actually contributing for a spin at site I? And the answer is that the number of spins which are contributing is 2 times the dimension of the space, because we are choosing hypercubic lattice. Hypercubic lattice means in every direction you have 2 neighbors, right? Okay, so as a result you have 2D neighbors. So that would give you a factor of 2D, and then you basically propose that since you see an average effect, okay, every side J gives you some average magnetization M. Okay, we had defined this magnetization in the following way earlier, that I hope I have defined. Maybe I'm going in the wrong direction. Yeah, magnetization is defined like this. So uh, so it is of course del F by del H, that means response of free energy to the change in magnetic field per site, because there is a 1 over n dividing it. Okay, so magnetization is really a per site effect that we are looking at. Okay, so per site you have some spin. Okay, like at site Sj, at site J you have a spin Sj. Okay, so this average value, if you are saying that that average value is a mean field, then you would say that that would be an average magnetic field. Okay, so therefore what you get is 2d from the sum J times M. That is what is Hi. Hi is equal to H plus 2d Mj. Okay, and the last term is being ignored. Okay, does that answer your question?
Yes.
Okay, any other question? Okay, so coming back to what we are looking at, that the formula that we are going to use is same as the magnetization formula that we used for when we looked at only the external stimulus talking to the spins of the system, because in the mean field approximation, the effective Hamiltonian, mean field Hamiltonian looks pretty much the same. Okay, except that the magnetic field is not just the external magnetic field, but external magnetic field plus some effective magnetic field. Okay, so we take that and plug it into this formula and replace tan hyperbolic h by kbt. There are sometimes I have just called it beta, but it's the same thing. Okay, uh, is tan hyperbolic beta times h plus 2d mj. Okay, now this makes an important change in the formula, because this contains m on both sides, and you may not have an answer to the, I mean, there may not be any value of m for which this equation would be satisfied. Okay, uh, typically that won't happen, but you may not have multiple values. At least you may have just one value. Okay, so we have to of course effectively draw left hand side, draw right hand side, and see how many times it cuts. Okay, how many times they are equal. Okay, so suppose you set external magnetic field to 0. Okay, then you get an equation which is m is equal to tan hyperbolic 2 times beta times d times m times j. Okay, fine. So we have made an assumption that there exists some effective magnetization uh, coming from all the spins acting on a spin sitting at site I, and now we are going to determine the value of that magnetization by self-consistently solving this equation. Okay, so mean field is basically determined self-consistently. Okay. Okay, so for simplicity, define kb times tc to be 2dj. Okay, if you do that, then you get you can make this expression look like m times tan hyperbolic m tc by t. Okay, is the equation that is equal to m. Okay, of course it has to be solved self-consistently, but only advantage of writing it in this way is to assign a critical temperature to the system, which is related to the uh, coupling of spins, and of course related to the dimension in which you are working. Okay, fine. So let's try to kind of plot this function. Okay, Suppose you look at this tan hyperbolic function. So let me not go up. I just want you to look at this function. Okay, but maybe I'll just roll this down now. Maybe this one. Okay, so suppose you are looking at this function. Maybe even simpler than that is this. Okay, suppose you are looking at this function and you want to plot this. Okay, left hand side is m, so that is this green straight line. Okay, I suppose you can see that. Okay, maybe I can kind of lower this a little. Okay, so this green straight line is the straight line corresponding to y is equal to m. Okay, so x-axis is m, y-axis is either left hand side or right hand side. Okay, so y is equal to m is this straight line, and this orange line is y is equal to tan hyperbolic m Tc upon T. Okay, for temperatures which are larger than Tc. Okay, so if the temperature is larger than Tc, then the argument of tan hyperbolic is m times a number which is smaller than 1. Okay, you agree with me? Is it fine? So if tan hyperbolic, say what I have chosen is like, in this graph I can tell you what I have chosen. I have chosen T by Tc to be 1/3. Okay, so if you are looking at tan hyperbolic 1/3 times m, okay, this is just to enhance the effect. It is not necessary to go to 1/3. You can take any number which is smaller than 1. Then the slope of the tan hyperbolic near m is equal to 0 is smaller than 1, because tan hyperbolic expands. Tan hyperbolic x would expand as x plus x squared kind of piece. Okay, so the leading behavior is x, but x has a coefficient which is a number smaller than 1 times m. Okay, so therefore it's a straight line uh, around origin, around here, but that straight line would have slope less than 1. Okay, if that line has a slope less than 1, and as you go out it is kind of going to flatten uh, and stop at total value to be 1 at infinity. Okay, then there is no chance of this orange line crossing this green line again. Okay, you agree with me? The tan hyperbolic with the argument, yes. Yeah, so if you have a tan hyperbolic with argument less than 1 times m, then that tan hyperbolic would not cross a straight line with slope 1 more than once. It will cross only at the origin, and after that it will not cross again. Okay. On the other hand, if you take this, of course, taking the argument less than 1 would mean that T is larger than Tc. Okay, and that is the phase we would have called, say, a paramagnetic phase. Okay, and that it is a paramagnetic phase is clear. Okay, it still has this tan hyperbolic behavior. Okay, but if T is less than Tc, then the argument of tan hyperbolic is larger than 1 multiplied by m. So it will be alpha m, where alpha is larger than 1. If it is larger than 1, then the slope of the line, which is, let's say, this turquoise line, okay, slope of that line is larger than 1. Okay, and therefore it would of course still cross the straight line, in the green straight line at origin. Okay, but the tan hyperbolic function asymptotically goes to 1. Okay, and whereas the straight line is of course going to cross 1 pretty fast compared to the tan hyperbolic function. So the tan hyperbolic function would cross the straight line once again. In fact, it will cross the straight line twice again. Okay, fine. So what you find is that besides m is equal to 0, at which this equation would be satisfied, there exist other values of m such that this equation would be satisfied again. Is this point clear? This is just a graphical way of seeing that if two functions cross each other, then at the point where they cross, the two functions must be same, right? Is this clear? Hello?
Clear, sir.
Yes, sir.
Okay. Just wanted to check. No, okay. Now comes the interpretation of these new points. Okay. So these new points tell you that you have an effective magnetization of the system, okay, which is different from zero. Okay. We would interpret this new state where there is some effective magnetization, okay, to be the ferromagnetic state. Okay. Now, why do we get two answers? Well, we get two answers because either the magnetization could be positive or the magnetization could be negative. Okay. That depends upon what was the external magnetic field that we wanted to use while we were kind of cooling the system from paramagnetic phase to ferromagnetic phase. Okay. If you apply the magnetic field in positive direction, you would land up at this configuration. If you had applied it in the opposite direction, you would have landed up at this configuration. Okay. But this configuration is in fact not a stable configuration. Okay. Uh, so there exists a stability analysis that you can do, and the stability analysis tells that if a function crosses the straight line from below, okay, then that point is not stable. But if it crosses from above, then that point is kind of stable. Okay, so that is a kind of configuration that you would have to do. Okay, here it would look like it is crossing from below, but actually it is not, because you have to take into account that you are looking at the negative value of the function. Okay, so if you look at the positive value of the function, you can kind of uh, make this statement very clearly. Negative value, you'll have to kind of just be a little careful with the signs of the function. Okay, fine. Of course, one can really study this function by doing the stability analysis. We'll write down a model which will actually tell us how the stability analysis can be done for this. Okay, but the point of this exercise is to say that if the temperature is less than Tc, then non-zero magnetization is more stable than zero magnetization. Okay, and therefore the system would prefer to be in the ferromagnetic state than be in a zero magnetic field, zero magnetization state. Okay, which could still be paramagnetic state. Okay, now of course, as I said, that like if you pick up random iron piece, it is not a magnet. Okay, but that it is not a magnet is for a different reason. It may have domains which are magnetic, but the domains pointing in different direction could cancel the effect, and therefore the effective magnetization is zero, but each domain has non-trivial magnetization. Okay, so any questions about this?
Does the magnetic material contain domains, sir?
Magnetic material also could contain domain. Okay, it is not necessary. It's like, for example, if you convert iron into a magnet, it does not mean that all domains inside the iron are all pointing in the same direction. It is probably just saying that the majority of magnetic domains are pointing in same direction compared to the other ones, the minor subset which is pointing in different direction. Okay, and in that case, if majority of domains are pointing in same direction, they effectively produce magnetization. Okay, and in fact, domains do form purely because of thermal fluctuation also. That if there is a sufficient amount of thermal energy available, some bunch of spins could just decide to point in a different direction. Okay, so at room temperature, a magnet would always have other domains with spin pointing in different direction. Any other question? Okay, so So the main point here is that in spite of doing a kind of drastic simplification of the original system and reducing it down to essentially Ising spin system, okay, and after that doing another drastic simplification by saying that, like, nearest neighbor interactions and all is not so important in picking up the essential feature of the system, and therefore we will only look at the what is called the mean field approximation. In spite of doing all this, we still manage to find that the system undergoes a paramagnetic to a ferromagnetic phase transition with non-trivial magnetization as the temperature falls from T greater than Tc down to T less than Tc. Okay, so in spite of so many approximations, mean field still managed to capture this feature. Okay. Okay, fine. Yeah, so we described all this. Okay, so let's try to kind of go back to the formula that we had, and the formula was uh, this one, okay, which is rewritten uh, by replacing beta by 1 over kt. Okay, uh, so if you look at this formula, okay, we can kind of use the property of the tan hyperbolic function. Tan hyperbolic a plus b is tan hyperbolic a plus tan hyperbolic b upon 1 plus tan hyperbolic a tan hyperbolic b. Okay, so use that property to write down this function in this particular fashion. Okay, it's just pure algebra. Okay, once you do that, then you could kind of invert this relation and write down tan hyperbolic h by kbt in terms of m and tan hyperbolic m by t times tc. Okay, so that is this expression, tan hyperbolic h by kbt is equal to m minus tan hyperbolic m divided by 1 minus m times tan hyperbolic m. Okay, that is a kind of expression. Everything is exact. If you assume this function, then all the calculation manipulations are still exact. Okay, this function itself is not an exact function simply because we have already done some approximation in the model, and the model itself is an approximation of the exact system and so on. So there are like levels of approximations being done. Okay, as long as it captures the correct and essential physics of the system, all these approximations are still reasonably okay. Okay, fine. Now remember one thing, which is something I had mentioned earlier but may not have emphasized sufficiently, that our interest, since we are looking at what is called critical phenomena, our interest is in studying the system close to the temperatures, close to the temperature Tc. Okay, so T is in the small neighborhood of Tc. Okay, so therefore we don't really want to push this behavior uh, like way out into, say, T very, very large or T very, very small or some such thing, uh, because we are really interested in studying the critical behavior of the system as to how the system actually undergoes the transition. Okay, that is what we want to really focus on. Okay, that is not to say that the ferromagnetic phase or paramagnetic phase is not interesting to study. They are interesting to study, but uh, our mandate is to study transitions right now. Okay, so if one wants to, of course, study ferromagnetic system at much lower temperature than transition temperature, the analysis would be of a different kind. One is not going to look at how the system actually undergoes a transition, but one is looking at how the system behaves at low temperatures. Okay, and that requires entirely different set of uh, kind of equation, different set of models. Okay, fine. So since we are interested in behavior close to Tc, uh, and also we had studied the system when H was set to 0 to find that there was a, sorry, wrong one was moved. Okay, which led to this kind of graph. This graph, of course, is when H is set to 0. Okay, let's try to ask, how does this expression kind of pans out when one is taking the external magnetic field to be small. Okay. Now the point is that, like, if the external magnetic field is small, then we could kind of expand these quantities on both sides. Okay. And the reason is the following, that we are looking at external magnetic field being small and temperatures close to Tc. Our system has the following behavior, again from this graph, that if you are above, uh, if the temperature is above Tc, then effective magnetization is 0. If the temperature is below Tc, then effective magnetization is non-zero. Okay. But the point is that if the temperature is just marginally below Tc, then this crossing point is very close here. Okay. And therefore, uh, the effective magnetization is non-zero but small. Okay. And we want to utilize this fact that it is small. Okay. So we are working at in the limit, say T less than Tc, but T less than Tc such that Tc minus T is a small number. Okay. If you do that, then you can expand both sides of this expression, and you write down the expanded expression to be h by kt is approximately m into 1 minus Tc by T plus m cube times Tc by T minus Tc squared by T squared plus Tc cube by 3T cube plus dot to dot. Okay. And then of course you have a higher order terms in m. Okay. So that is the kind of behavior of the system. Okay. In the small magnetic field and close to the transition temperature. Okay.
Here are we assuming that M will also get very small?
Yes, m
That,
will be small. That is what I was trying to say. That if you are above Tc, then m is 0, because that is the only point where the orange graph crosses the green graph. Okay. But if you are below Tc, which is what we want to look at right now, okay, then m is non-zero. Okay. But this graph, I have chosen the Tc by T to be 3. Okay. So if Tc is 1044, okay, then T is something of the order of like 370 or something like that. Okay. Fine. So it is way below the Tc, but that's not what we want to look at. We want to look at, like, if Tc was 1044, we are looking at T of the order of say 1040 or 1035 or something like that. In that case, this orange line is slowly kind of deforming upwards and crossing this yellow line from below, and then it kind of crosses over back uh, kind of and be lower than the green line. But so for a small duration it will be above green line, and again it will kind of be below green line. Whenever it crosses the green line, that is the effective magnetization. And if Tc is like just Tc, I mean, let me use this notation called Tc minus. By Tc minus, I mean the temperature is almost like equal to Tc, but from the lower side. Okay. So imagine like 1040 versus 1044 or something like that. Then the other solution, the stable solution, is small magnetization. That is what is being used. Okay. And in that case, you can, yes.
Yeah, yeah. Even for T greater than Tc, we have a positive solution, right?
No, no. If T is
If you
greater, yes,
if you plot it like m, the LHS is the same straight line.
yes,
At m equals 0, the tan hyperbolic is some positive constant, which is tan beta h.
yes.
At
Oh,
hm, I'm taking to be positive.
when you are taking the sorry, I did not understand what you are saying. I am plotting this with h is equal to 0. External magnetic field is 0.
Yeah, yeah. Then we have only one solution when T is less than, when T is greater than Tc, we only have m equals 0 solution.
Exactly.
Yeah.
Yeah.
But after, like, the analysis that you're doing later on when you're taking some finite h,
Yes.
in that case, even for T greater than Tc, we'll have a positive m solution.
Certainly, that I agree. But that is
Yeah.
because that magnetization is induced by external magnetic field.
Yeah, possibly.
Yeah.
I mean, yeah.
Yes, not
Then
possible. Exactly because of the external magnetic field.
Yeah, so in that form, we do not have to restrict T less than TC. I was saying that what we are expanding later on.
That is right. So this expansion, right? This expansion?
Here T is something like maybe near TC, but not lesser or higher than TC. Yeah.
That is right. That is because if I, but what I want to do is that I want to keep external magnetic field very small. Okay. If my external magnetic field is large, then I cannot keep a linear term here, right? Because
Yeah.
tan hyperbolic also has many other terms like h cube pieces and so on. So if h is large, then h cube is larger than h. Okay. So we cannot do that. Okay. So what I was trying to say was that if you take magnetic field small, then to leading order you can do an expansion like this on the right hand side also, because the effective magnetization also would be small. Okay. And your point is well taken that the magnetization would be non-zero little above TC also, simply because the external magnetic field is inducing it. Okay.
Yeah.
Yeah. So, but that is just within the small range. One is not really kind of going way out into higher temperatures. Okay. So in the neighborhood of TC, this expansion makes sense. Okay. For small external magnetic field. Okay. Is that fine?
Yeah.
Okay, so now we will kind of use this relation and study the behavior of the system in the neighborhood of the critical point. Okay, and that study is what is called computing critical exponents. Okay, now these objects are called critical exponents because we are studying the behavior of the system in the neighborhood of critical point. Okay, that is how it actually acquires this name. Okay, fine. So in our case, of course, we are looking for critical exponents of a system which is undergoing transition from paramagnetic to ferromagnetic state. Okay. Of course, you could have critical exponents for various other things like liquid gas phase transition. In that case, you would have critical exponents of a different type because you don't have magnetization as a quantity that you want to define. Okay. You want to look at probably the density as the right kind of object to look at when you look at liquid gas phase transition. Or if you want to look at, say, phase separation, you have two different liquids, say water and oil, and they are mixed into a single liquid at some temperature, and at some lower temperature they would phase separate. That water will be kind of on one side and oil would be on the other side. Okay, then for that you would have another kind of variable that you would want to study. Okay, in our case, of course, we are going to look at the transition from paramagnetic to ferromagnetic transition. Okay, fine. So if you are looking at a system which is in the absence of external magnetic field, okay, so let me get my equations kind of right up there, but let me kind of keep it steady like that. Okay, fine. So if you look at the situation where the external magnetic field is 0, that means left hand side of this equation is 0, then the magnetization that you would see would have three solutions. Of course, one solution is m is equal to 0, okay, because this right hand side is equal to 0. So m equals 0 is a solution, obviously, which of course we know from the plot also that m equals 0 is a solution. The other solution is m squared is equal to 3 times Tc minus T upon Tc. Okay. So you can kind of check, you can manipulate this expression to see that this is the answer. Okay. One way to do that is to realize that if you take 1 over T cube outside, then these terms are forming almost a cube of Tc minus T. It's a Tc minus T cube term. Okay. Except there is no T cube term on the numerator. So you can kind of add a T cube piece to Tc minus T cube. Okay, but then that T cube piece will cancel the T cube, and therefore the final answer is that a Tc minus T cube divided by 3T cube plus 1/3. Okay, And therefore at the leading order, it is the 1/3 which contributes and not Tc minus T cube by T cube. Okay, that is the leading contributor at the cubic order, which is 1/3. Take that across and you get 3 times Tc minus T upon Tc. Okay, that is the expression. Okay, fine. So this behavior allows us to define the first critical exponent. And this critical exponent is defined in the following way, that as you take the temperature T to Tc from below, okay, that means temperature is less than critical temperature, and as you take temperature T to Tc from below, holding the external magnetic field to 0, then M, the magnetization would go as T minus Tc to the beta. Okay, maybe I should have written Tc minus T to the beta, really, because I'm taking Tc minus T to be positive. Okay, I'll correct that. So it is written as Tc minus T to the beta, and from this expression we find that the beta value is half for the mean field theory. Okay, because m squared is proportional to Tc minus T, so m is proportional to square root of Tc minus T, so beta is half. Okay, so we have found the first critical exponent, and that is that the magnetic field, sorry, excuse me, the magnetization as a function of temperature behaves like this. Okay, behaves like Tc minus T to the half. Okay, fine. So we can plot that also. Okay, so it would look like this. That so I'm plotting magnetization along y-axis and temperature along x-axis. If the external magnetic field is 0, above Tc there is no effective magnetization. Okay, so therefore this plot has to basically go down to 0 at T equals Tc. Okay, how does it rise? Well, that rise is actually parabolic. Why? Because as a function of T, m goes as m, I mean T as a function of m goes as m squared. Okay, that's why near T equals Tc, this looks like a parabola. Okay, that was our equation here, right? Near Tc, it is parabola. It depends on m squared. Okay, so that is the behavior, but that behavior is capped by the value of the maximum value that a spin can take, namely 1 or -1. Remember, the magnetization is defined to be del F by del H times 1 over n. Okay, there is a minus n also, but it is a 1 over n that is important because that gives the correct normalization to the magnetization. If all the spins point in the same direction, that would give you the maximum per site magnetization, and that would be either +1 if all of them point up, and or it would be -1 if all of them point down. Okay, so therefore, although it starts off as a parabola, it kind of slowly flattens and stops at m is equal to +1 or -1. Okay, so that is the kind of behavior that we would get, but we are not trying to describe this curve. We are trying to describe the behavior of this curve near Tc, and that is parabolic. Okay, and that factor is half, exponent is half. Okay, the second critical exponent is defined to be delta. Okay, uh, these are not, these nomenclature is not my choice. This is a kind of legacy thing in the field of critical phenomena. These are the parameters which are used universally. So if you tell somebody who works on critical phenomena that I'm looking at critical exponent beta or delta, that person knows exactly what you're looking at. Okay, so it is universally defined. uh, I believe all books use the same notation. Okay, so the second critical exponent that we want to look at is what's denoted as delta, and that is defined as how does the magnetic field depend on the external, sorry, magnetization depends on the external magnetic field. Okay, so if you turn on an external magnetic field, what is the rate at which the magnetization will take off? Okay, and that is what you want to do at T is equal to Tc. Okay, so if exactly at the transition point, you're trying to see how the system responds to external stimulus. Okay, now again, let's look at the expression written down here. Okay. If you set t is equal to Tc, then this term is gone. Okay. So the linear piece is out. Okay. And therefore H actually depends on MQ. Okay. So therefore we find that the mean field value, the value of delta within the mean field approximation is 3. Okay. Because it directly starts with Q. Fine. You can also check that if you set t is equal to Tc, this expression doesn't vanish. Okay. Otherwise, like, it would have gone to the higher power in M. Okay. But it doesn't vanish here. Okay. So, so we have found the second, we have defined the second critical exponent and we have found its mean field value. Okay. The third one is the magnetic susceptibility. Magnetic susceptibility is a response of magnetization to the change in external magnetic field. Okay, so you have a system which has certain magnetization. This magnetization could be spontaneous or it could be a magnetization due to external magnetic field. Okay, in other words, we will check the susceptibility of the system both at t less than Tc, where you may have spontaneous magnetization, but also for t greater than Tc, when you do not have spontaneous magnetization, but you may have magnetic field induced magnetization. Okay, you want to ask a question: what is the rate of change of magnetization as you change the external stimulus? Okay, that behavior is what is called the susceptibility. How susceptible is the magnetization of the system to the external uh, stimulus? Okay, so here's the equation 2 again. And so to determine chi, we will differentiate this expression with respect to H. Okay, that will give you del M by del H at various places, right? So let's look at that. Okay, so if you differentiate that, then of course H goes away from the left hand side. Okay, but then you get a chi times 1 minus Tc by T, and then you get 3m squared times del M by del H, which is chi again, times of course whatever is in the parenthesis. Okay, is that right? So from this we can now determine how the chi would behave. Okay, how this what is the response of the system when you change the magnetic field. Okay, so if the temperature is larger than Tc, then system is in paramagnetic state and there is no spontaneous magnetization in this case. Okay, fine. So because there is no spontaneous magnetization, you can set all these pieces on the which we depend on M to 0 basically, and you just look at the first piece. Okay, and that tells you that your chi would go as 1 over T minus Tc. Okay, you can just take 1 minus Tc by T across on the other side. Okay, up to this kBT factor and so on, you get this answer. Okay, so these are all approximate relations. There are some numerical factors sitting around in front. We are really trying to see how they would behave as a function of variables and not look at the dependence on the constants. Okay, unless it is really essential. Okay, there is some place where we would say that the constants are different. Okay, fine. So what you find is that chi goes as 1 over T minus Tc. Okay, from here. Now let us define a critical exponent gamma to be chi going as T minus mod of T minus Tc to the minus gamma. Okay, the mod is not really essential, but nevertheless that is how it is defined. Okay, this is a definition for T greater than Tc, and that is the reason why you really don't need a mod. There is another definition when T is less than Tc. Okay, which we will give again. Okay, shortly. But the way it is defined here, you can compare that with the mean field computation, and you find that the mean field value of gamma is 1. Okay, because it is defined to be minus gamma, so gamma is 1. Okay, we could do the same thing in the ferromagnetic state, and in the ferromagnetic state, T would be less than Tc, and we need to massage this expression a bit by using the behavior of M, which was square root 3 times t minus tc to the half. I'm sorry, I forgot to put the square root here. But or let me say m square is equal to 3 times t minus tc upon tc. You can plug that up into equation 2, and you find that, or rather derivative of equation 2, that is the equation that we had obtained some time ago here. Okay, you can put m squared to be that quantity, and you find that chi still goes as 1 over t minus tc. Okay, the coefficient is different, but it doesn't matter. Okay, what you find is that chi below tc also has similar behavior. Okay, and therefore if you define the critical exponent below the transition temperature, that chi goes as t minus tc modulus to the minus gamma prime. Okay, then the gamma prime turns out to be 1 again in the mean field approximation. Okay, so we have determined 4 critical exponents so far: beta, which was half, delta, which was 3, and gamma prime both were 1. Okay, so those are the 4 critical exponents which tell you how the magnetization and the magnetic susceptibility behave in the neighborhood of critical temperature T equals Tc as a result of small changes in the temperature, which is kind of thermal what is it called, thermal probe, or a thermal stimulus, or external magnetic field, which is like a magnetic field probe or magnetic field stimulus. Okay, and we have used these 2 things to determine these 4 critical exponents in the neighborhood of Tc. Okay, we can compute specific heat of the system. Okay, and the exponents corresponding to the specific heat of the system are defined in the following way. C is proportional to T minus Tc to the minus alpha if temperature is larger than Tc, and it is proportional to Tc minus T to the minus alpha when temperature are less than Tc. Okay, so that is just the definition. Okay, now we can determine this behavior by studying the magnetic energy of the system. Okay, so what is the magnetic energy stored in the system? We'll first derive that, and then using that we can derive the specific heat of the system. Okay, good. So the magnetic energy is of course proportional to the external magnetic field plus this effective magnetic field generated by the average values of the neighboring spins, okay, times the magnetization itself. Okay, right, because dimensionally that is what you have, h times m or h times s. If you take the average value of s, then average value of s is m itself. Okay, so therefore this is the magnetic energy. Okay, the original system has various other contributions to the energy also. There is a thermal energy available, there are energies coming from the conduction band electrons and stuff like that, like phonon energies and so on. We are ignoring everything of that type. We have a rigid lattice on which only Ising spins are sitting around, and we are asking questions only of that subsystem, and that's why I chose to call it magnetic energy, just to distinguish it from the total energy of the system. Okay, fine. So if you take T greater than Tc, then it and set H equals to 0, then the magnetic energy would just vanish, because for T greater than Tc, in the absence of external magnetic field, spontaneous magnetization is 0. Okay, and therefore the magnetic energy is 0. Okay, fine. So that would be the behavior of the system. Okay, on the other hand, if T is less than Tc and if you set the magnetic field to 0, then you can show that H effective times m goes as roughly as m squared. Okay, but m squared is proportional to T minus Tc. Okay, we had derived it. Okay, that expression is same as m squared equals T minus Tc nevertheless. Okay, m squared is equal to T minus Tc. Okay, so So because it is minus m squared, it should be Tc minus T, but minus m squared would be T minus Tc. So E goes as T minus Tc, and the specific heat is the response of the energy to thermal fluctuation. Okay, and therefore you can differentiate that, and you will find that the specific heat is constant. Okay, now of course specific heat was constant for T greater than Tc also. Okay, only difference is that this quantity was constant and zero, whereas this quantity is constant and non-zero. Okay, so therefore you see that the specific heat is discontinuous. Sorry, we find that the specific heat is discontinuous across the transition. Okay, but that is not what we are looking at. We are looking at how is it a function of T minus Tc. Okay, and alpha is that exponent. Okay, it is the exponent of dependence of the specific heat on the delta T in some sense. Okay, now that dependence doesn't exist. Okay, in the mean field approximation you find that alpha and alpha prime are both zero. Okay, is that fine? Hello.
Shouldn't C also be like infinity or something like that, because there is a phase transition at T equal to Tc?
Yeah. So yeah, that is true, but the mean field theory doesn't see it. Okay, so actually what is going to happen is different. In reality what happens is different from what mean field theory sees. Okay, so that is why I was saying right in the beginning that the model that we are going to study is crude model. Okay, it kind of glosses over many details of the system, but it at least manages to capture one essential feature, namely it shows that the system has spontaneous magnetization. Okay, is it making sense?
Yes.
So therefore, whatever critical exponents that we have obtained, like for example, half and 3 and 1 and so on, okay, these are all mean field values. Okay, uh, uh, I will kind of tell you what are the real values, maybe not in this class, or maybe I can tell you, although it's not there in my notes, but I can tell you what those values are. Okay. Just give me a moment. Yeah. So I can tell you those values in a moment. Actually, pretty close to the end of my notes today. I kind of finished a bit faster this thing, but nevertheless. So what I was trying to say was that you get alpha and alpha prime both to be zero. Okay, uh, in the mean field approximation. That is not to say that the system actually has alpha and alpha prime equals zero. Okay, but the mean field approximation sees it to be zero. Okay, so what we saw today is essentially a set of definitions which defined the critical exponents alpha, alpha prime, beta, gamma, gamma prime, and delta. Okay. Besides that, there are two other critical exponents, nu and eta, which we will look at soon. It requires studying how the fluctuations in the system are correlated. That you look at a spin, one particular spin in the system, and you kind of disturb that spin, and you look at some other spin at some other lattice site and ask, does the spin at site J see the effect that the spin at site I is fluctuating? And J is not necessarily a nearest neighbor. J could be reasonably far away site on the lattice. You want to ask a question, how far is the fluctuation? I mean, you disturb one particular spin at site I, okay, how far that disturbance reach, okay, and we want to kind of quantify that in the neighborhood of t equals tc. Okay, so that would require giving a couple of definitions again, and actually compute a quantity so that we can read off nu and eta. Again, one computation can be done in within the mean field approximation, which we will do at some point. Okay, and of course that would require improvisation. Okay, so anyway, so these objects are called critical exponents, and as I said, that this name is derived from the fact that all these quantities are derived from the behavior of the system in the neighborhood of a critical point. Okay. Now, one important thing that I should have mentioned throughout this discussion was that if you notice how the system behaves, or how all these quantities behave, they all have some power law behavior. Okay, m goes as tc minus t to the half, or chi goes as tc minus t to the minus 1, and stuff like that. They all go as power law. There is no exponential fall of pieces sitting around. Okay, you could have said that, like, okay, if chi goes as t minus tc to some power times exponential of minus something, like minus t minus tc kind of thing, then it is the exponential piece which would have dominated the entire game, because the rate at which the uh, susceptibility function would fall would be completely determined by the exponential function. Okay, and these kind of power law behaviors would have been subleading effects. Okay, you really have to kind of look at special uh, details of the system to be able to pick out these kind of pieces if there is an exponential sitting around. Okay, the exponential function sits around in the system whenever you have a scale in the system. Okay, for example, if you have a particle with mass m, then the correlation function, or the influence of that particle, falls off as e to the minus m times r. Okay, massive object, effects of massive object fall off as 1 over uh, exponential minus mr. Okay, falls off exponentially fast. Okay, effects of massless particles fall off as power law. Okay, for example, the Coulomb potential goes as 1 over r, or gravitational potential goes as 1 over r, and so on. Okay, so the important point here was that none of these quantities have any exponential uh, damping or exponential envelope which are kind of smothering these effects that the power laws have. Okay, and this is the important feature of the critical systems or critical points, that at that critical point you do not, the system is scale invariant, it does not have any scale. Okay, anytime the system has a scale, the system various quantities fall off grow or fall off exponentially fast. Okay, so what we are looking at are the class of systems which are called systems which are scale invariant. Okay, so that is the class of system that we are looking at. Okay, now of course, uh, if you are studying it in arbitrary dimension d, then so far at least we do not have any counter example that any theory which is scale invariant is also conformally invariant. Okay, so the theories that we are really looking at are what are called conformally invariant theories. Okay, but I would just want to be to err on the kind of safer side and call these systems only scale invariant theories. Okay, they do have conformal invariance, but there is no proof of it, at least in d greater than 2. In two-dimensional systems, there is a proof which says that if your theory has a scale invariance, then you necessarily have conformal invariance. Okay. In recent times, there have been some attempts to show counter examples in higher dimensions, in d equals 4 or, and 5 and so on, that you could construct theories which are scale invariant but not conformally invariant. But I don't think those counter example actually held ground. Okay, they quickly realized that there was some flaw in the argument, and I don't think it has worked. Okay, so but there is no clear mathematical proof which says that if your theory is scale invariant in d dimensions, then it is necessarily conformally invariant. Okay, so coming back to what I was saying, it's kind of I'm at the end of the lecture really, that we have derived, we have rather not derived, we have defined a set of yes.
We have overshot today. Can we do this?
Oh,
Because condensed matter has just started.
oh, sorry. Yeah. Okay. Okay, fine. So I'll stop at this point. I somehow thought that I have kind of.
Okay.